Hello, everybody. My name is Christian Bluechel. I'm the CTO of Next. I'm located partially in Singapore and in Switzerland, where we do the technical developments of our portable hemodialysis device. And I'm going to tell you a bit more about the functional overview of the device and what is special about the device over the next 15 minutes. So, as mentioned, our device is a portable hemodialysis device, but hold on, I'm not in the presentation, but we are not the first ones doing portable hemodialysis devices. In fact, they have been around some 40, 50 years ago. They have been around and they have been quite extensively used. Like you see this gentleman here on the left who is carrying a portable sorbent-based device in his Volkswagen bus. And apparently this patient treated himself with the device over the course of 30 years. The machine that you see here was in use for a total of 4 decades. It was used in over 6 million treatments and it was very mobile. As you can see, it was used in caravans. They had a small version that could be carried around, and it was even used in things like on a sailing boat. And this is something, when you think of it, it's something that from today's perspective is completely unimaginable, doing hemodialysis on a place like a sailing boat. But at that time, 40 years ago, it was actually quite imaginable. It was okay. People, yeah, why not? They did it. And this is where we want to get back again. We want to have something that is so independent and so standalone that it can be used in all sorts of places. When we look at what is called portable today, then the most portable machines would be the three on the left. So you have the next stage, you have the Quanta, and you have the Feasibility machines, all of which are single pass machines. So I get a bit more to that in a minute. The important thing is the fluid to treat the patient's blood is only used one time and then goes down a drain. If you really want to be portable and to be completely independent, you need to regenerate dialysate. That is what really decouples you from all the infrastructure requirements, from the requirement to be connected to a water outlet or a drain. And this is what really makes the difference between something that is transportable to something that is actually really portable and in extension even wearable. This is something that will come in the not so far future, and all the machines that you see on this picture here are already in clinical trials. So this is something that is really happening. The key difference here is on the left side you see a conventional single pass hemodialysis. So the machine is connected to a water outlet or to a large number of bags. Then the fluid is used one single time to treat the patient's blood and goes down the drain. And this makes the machines very large and bulky, and they need quite special infrastructure requirements. They have a very high power requirement because you need to warm up all this fluid that is being used for the treatment. They also need to be connected, as I mentioned already, to a water outlet and to a drain, and all that fixes them to one fixed location. This, what I wrote here, is of course specially made for home dialysis. So if a patient wants to use this at home, then basically they have to convert one room, which then almost looks like a hospital room. And in stark contrast, on the right side, when we regenerate dialysate, then you only have a very small volume of dialysate, which is used over and over again. And this, once it's warm, you don't need to heat it anymore. So the energy consumption is very small, and it has a complete freedom of location because you do not need to be connected to all these infrastructure things like on the left side. Our sorbent is using a technology which is still remotely related to that of that first machine that I showed on my first slide, to the ready approach. And what this means is that we have spent dialysate coming from the dialyzer, that is the yellow line, which then passes through our regeneration filter, our cartridge. And then what comes out of here contains no more toxins, but also no more electrolytes. There's no calcium, magnesium, and potassium. So the outflow of the cartridge is essentially a solution of sodium chloride and sodium bicarbonate. And this has then to be reinfused with an additive solution. This is like a concentrate containing calcium, magnesium, and potassium. This is redosed into here, and after that, the dialysate is fully regenerated and is ready to be reused again. And then the cycle continues over and over again. The cartridge contains a number of key ingredients, which are also still related to the original ready approach. Importantly, there is urease. Urease hydrolyzes urea into ammonium and bicarbonate. And then the ammonium, together with other cations, is bound in a cation exchanger, which is zirconium phosphate. And then we have an anion exchanger, which is called hydrous zirconium oxide, which primarily binds phosphate. And we have activated carbon, which binds basically all the other molecules that are there. In our case, the urease is covalently immobilized, and so it cannot be washed out of the cartridge, and it allows us to have a homogeneous mixture of our solvents. Now I'm going back to this predecessor device, the ready system, and anything else which happened after that. So for the last 4 decades, solvent dialysis has always been afflicted with a very poor control of the dialysate sodium concentration. The black line you see here is the sodium concentration in dialysate. There was a constant and significant release of sodium from the cartridge during this regeneration process, and in order to compensate that, one had to start the treatment with a very low sodium concentration, 120, and then there was a gradual steady increase over all the time and ended up at a high concentration of 160 millimole per liter. What we have managed to do is we have managed to get rid of this old dogma. We have found a way to improve the solvent, to reconfigure differently. It's a technical detail. It's part of our secret sauce. We have managed to get a flat sodium profile. That means we have managed to find a way to teach the solvent cartridge to not change the sodium concentration during regeneration. That means after regeneration, the sodium concentration is the same as before. And the sodium concentration before is actually also equilibrated with the patient. So it came from the patient after equilibration with blood. And that means that the regenerated dialysate has the same sodium concentration as the patient's plasma. And that is what allows us to do something that is called isonatremic dialysis. Sorry, I thought I have an additional slide here, but it's quite an important point to mention. It's isonatremic. That means the patient receives a dialysate that has the same sodium concentration as the patient's plasma. And that is generally deemed a big advantage and is very difficult to achieve with conventional machines. Our machine does this all by itself. So now to our machine itself. You can think of the machine as being built up in a modular way. So you have the left half, which contains the blood circuit, and the right half, which contains the dialysate circuit and also the solvent cartridge. Both circuits have pre-assembled tube sets, which you can load very easily. So this is very user-friendly. You see slots in the front of the machine. You slot in the cassette, and then it's loaded by itself. And that's pretty much all the patient has to do. Then there's a detachable tablet, which the patient can take with them. So they can put it next to them wherever they are sitting or lying. We only have a total requirement of 4.5 liters in total. So this includes some fluid to prime the system, and then another 2 liters of that concentrate solution that I showed you in the beginning, the calcium, magnesium, and potassium solution. That's all that is needed in order to have a full-blown treatment of 36 liters of dialysate. Our machine currently is optimized for short daily hemodialysis, which means it's optimized for a treatment of 2 hours of dialysis per day. That said, and I can imagine that in your type of applications, you will need longer therapies. That is in the pipeline and will come maybe 1 year later. After the first product that we bring on the market will be the short daily hemodialysis for 2 hours, but then we can also have longer treatments of 4 hours or even longer. Importantly, also we can use any off-the-shelf dialyzer, so whatever the patient or the physician prefers can be used for this kind of treatment. So the machine weighs only 13 kilos, 1-3, and fits into a cabin luggage. So it is so small that it fits into that luggage that you usually bring with you into the plane. You can put it above your seat if you travel by plane. And it's very small and compact. You know where it is. We have done this multiple times, so it is perfectly doable and it works. As mentioned, it only requires 4.5 liters, but one of the things that I personally find is about the most important advantage of our device is that we are fully cardiac floating. The machine is electrically so isolated that we do not need grounding. Just a normal 2-pin connector is sufficient. We do not need earthing or grounding for safety of the treatment. That means you can really use any power plug. So wherever you are in your own house or on the field, you just have a generator, you can use this, it's no problem. Or in a hotel room. Just a 2-pin, whatever you can use to charge your mobile phone is also good to power our machine. And this gives you the ultimate freedom. And again, this slide deck is primarily directed for home dialysis. So you can really use the machine at any place in your own home. You don't have to worry about the power outlet. You can use it when you visit your family in the family's home. You can use it in a hotel, but as I mentioned, you can also use it out in the field. A functional overview, we have a few accessories and consumables. So first of all, there's this tablet that I already mentioned. Then we have the fluids. We have disposable sets, one for blood and one for dialysis, the dialyzer and the solvent cartridge. And there are also compatible accessories which connect via Bluetooth. There's a body scale. So the patient steps on the weighing scale, and then the machine already knows or proposes how much ultrafiltration has to be removed. And there is a wireless blood pressure sensor which can monitor at regular intervals. We also have the interface for the red sense disconnection sensor here. So in case there's external blood leak. Those are the dialysis sets. Not sure if I should go into details here. So we use a pump technology which comes here from Switzerland. It's pre-assembled peristaltic pumps, and this makes the system very robust and very user-friendly and also very accurate. So this is the dialysis set. We have 3 pumps, 1 pump going into the dialyzer, 1 pump coming out. The ratio of the 2 determines how much ultrafiltration is being removed. And then there's a 3rd pump for our additive solution. And on the blood cassette side, there's only 1 pump which drives the blood flow. Then we have all the normal safety features. We have the pressure sensors, the bubble detectors. It's all like what you would see and expect from a normal hemodialysis machine. We have already used this clinically. Here on the right side, this was the actual setup being used in our clinical trials in France. You see the machine is just standing on a trolley, and that is really all you need. So you imagine the machine here, then you have just 1 cable to go into the power outlet, and you can start your treatment. That's really all. Then, I mean, the patient has to come, and you connect the patient. That's all you need to do. In this trial, currently, we had a total of 7 patients that have been treated with our solvent. In a total of 28 therapies, it was quite a wide range of patients from 50 to 110 kilos, equipped with fistula graft and also catheter. So our machine also works with a central venous catheter. The toxin removal efficacy was similar or better to the conventional treatments that we used in comparison here. The patients did not experience any difference between their common conventional treatment and ours. We were all very happy with the treatment. Our biochemistry was exactly as intended. However, we found that some slight corrections were necessary, and they are already implemented. And currently we are preparing for a larger trial, which is then aiming at getting CE marking. And we want to start the CE marking process by the end of next year. So the large clinical trials will start later this year. expected to take about 1 year, and then we want to go to CE marking. And that's my presentation. Thank you very much for your attention. And well, I'm not sure if there's no questions, I guess, but maybe you have some questions on your side from the
Yes,
organizers here? Yes.
yes, we have some questions.
Okay.
And the first question, when we can expect to use this new technology in our patients?
So again, the first configuration that we will put on the market will be short daily hemodialysis. So 2 hour therapies intended to be used 4 to 7 times per week, depending on the patients. And this we expect to be ready for the market by the end of next year or early 27.
So we are happy to hear that probably we can start this technology in our patients, isn't it?
Yes. So, I mean, by the time it would be CE marked, again, it would be by the end of next year or early 2027.
Thank you, Christian. And one more question.
Hmm.
Uh, we are interested, is it possible for the patient to do this hemodialysis by himself? Look like our patients do the PD with automatic PD. And do they have this facility with your technology?
Yes. So it is decidedly intended for autonomous dialysis. So it can be used with an assistant. So there's a possibility that a nurse or a trained partner helps you set it up, but it is really intended to be used autonomous by the patient themselves. And so what is required here usually is a training phase, which usually takes 2 weeks. So the patients will be trained for 2 weeks to use the machine and do everything independently. And as you can imagine, the thing that probably needs most training is really the self cannulation. But that is not different from other machines that are already used in home hemodialysis today. Apart from that, our machine is very user friendly and will be very easy to learn. The nurses that we have trained so far, they learned it in 2 sessions.
Okay, thank you. And the last question is, are there any restrictions with using some different dialysators? For example, is it possible to use extend dialyzer or something else with a great surface of membrane or the new possibilities?
No, the dialysate is fixed. So the machine regenerates the dialysate. So what we regenerate here is a bicarbonate buffered dialysate. So it's fully bicarbonate buffered. It's a hemodialysis, and our current version has a fixed concentration of 2 millimole per liter of potassium and 1.5 millimole per liter of calcium. Later on, one can imagine that we can propose different electrolyte composition. So some patients may require 3 millimole potassium, for example, but we take it step by step. So for the time being, the first product will have this fixed dialysate composition.
Thank you so much, dear Christian. We very much appreciate this possibility to have a lot regarding this new technique and hope that we can start to use it in the nearest future.
Yes, very good.
Thank you so much, Christian.
Thanks, Dimitri.
Okay, thank you very much. My name is Azlan Hamzan. I'm from the Institute of Microengineering and Nanoelectronics, IMEN, University Kebangsaan Malaysia. And I'm glad to present to you today for the Rena Nexus Digital Summit and Roadmap to the 20th winner on some work that we are doing and what we have done in Malaysia to improve the condition of peritoneal and dialysis patient in Malaysia. So I'm going to give you a short presentation on wearable peritoneal dialysis device. So perhaps I'm going to explain a bit on the model itself, how we develop biomedical innovation in Malaysia, and how it transferred down to institution, a research institution, and how we can translate that into a usable product, biomedical product that solve problem of dialysis and kidney failure in Malaysia. Okay, so I'm from the Institute of Microengineering and Nanoelectronics, IMEN, in UKM, University Kebangsaan Malaysia, Bani. The whole building on the right is our building, and we have a full-fledged clean room. Level G to level 2 is our clean room, and the rest are 18 labs that integrated into our institute. And we established in 2002, and we are the first MEM microfabrication clean room in Malaysia. And our research area is actually microengineering and nanoelectronics. We have 18 research field interconnected labs in IMEN, and we connect with more than many premier institutions all over the world, and we graduated more than 200 PhD and MSc up to 2025. We are the Higher Institution Center of Excellence from Ministry of Higher Education Malaysia, and we are Nano Malaysia Center of Excellence from Ministry of Science, Technology and Innovation Malaysia. And we do research in MEM for biomedical device, especially artificial kidney. Okay, so our institute focuses on 5 different niches. The most important one is MEMS and NEMS and nanoelectronics, and is supported by organic and printed hybrid flexible electronic group, and also microelectronic packaging and material group, micro and nanoelectronic system, MINDS group, and nanophotonic and quantum electronics group. And these are the research field and expertise that we have in our institute. Each of the square represent the researcher and the research project that we work on in terms of MEMS, organic printed hybrid flexible electronic, MEMS packaging, MindPack, micro and nano system, MINDS, and nanophotonic and quantum electronics. So these all translate into the product later on. And we have around 30 researchers, academic fellows, and around 20 support staff. We are 50 strong institute, and we collaborate with many professors and adjunct professors around the world, from the Far East Asia, JAIS, Seoul National University, and CPU, and Europe, of course, with you guys, and UK, France, Australia, Switzerland, and so on. And we also have some of the visiting fellows that's coming all over the world. IMEC, for example, EDS, and Griffith, NUS, and so on. And what our institute do is we want to translate our research patterns into usable product. And usually we take around 10% of the product that we want to translate into commercialized product and licensed technology. For example, this is taking last year's data. We have 27 patent filed and 16 granted, about 40% granted within the year, and 10% of that we try to translate into commercialized product and licensed technology. If we look at the direction in line with UN SDG, Sustainable Development Goals, we are focused on good health and well-being, affordable and clean energy, and also sustainable city and communities. From there, we propel down and focus. This is 1010-9 STIE, is the focal point of the Malaysian government in terms of the technology on the left, and also the areas that socio-economic drivers that the government want to focus on. So we focus on sensor technology and advanced materials, and those two core technologies is applied on energy sector, medical and healthcare, and also smart cities and transportation. So what we want to focus now today is on medical and healthcare. So this is how the project and also the development of technology is propelled down the tiers. So it started from the technology drivers, from the directive of the Malaysian government, and socio-economic drivers, essential technology, advanced material, medical, healthcare, energy, and smart city. And the trust is electronic device and system, and we go down to the enabler level, which is the wearable electronics, and we disperse the technology to the commercialization partners. In this case, for artificial kidney, Bluechel Group and Elna Group for our institution. So, talking about artificial kidney research in IMAN, we started the research back in 2008, about 15 years ago, and around 2012, we produced our first membrane that we tested on biological fluid. That was intended to filter particulates, small particles in hemodialysis. This is actually a membrane-based, silicon membrane-based filters that we made. We did KOH as the first stage of the filtration, and then we create small filter, smaller than the size of blood cell, to let the biological fluid pass through without letting the blood cells passing through them. And that has been the initial stage of our research. And then we create that in mind that we would reach artificial kidney in 20 years. So doing that, the government give a good support. In this picture, actually the woman in the center is actually the director, Deputy Director General of Health of Malaysia, and next to her is another lady, which is the Director of Medical Research, and also the top gun of medical research in Malaysia. I was the Deputy Director of IMAN this time. The center was my director that time, and we lead this project, the portable dialysis project, in 2017. It's actually top down. It's driven by the government, and the problem was presented to us on what to solve by our nephrologist. The very left guy in the picture is actually our nephrologist, lead nephrologist in our university hospital. And the doctors presented us a problem to unclog the patient build up in the wards. So what we think that we should do is we need to start on top of fundamental research, research on kidney filtration, solvent technologies, and so on. We do need to work backward as well, meaning taking back from what we have in the current dialysis technology and miniaturize it. I think we are pretty good at miniaturizing because we are Institute of Microengineering. So we make all devices micro size. So we would like to see how we can reverse the technology and meet in between later on. So we create a platform that's more reliable, portable, and hopefully later we can embed all our sensors and system into the created platform. So we think of portable dialysis as a way to move forward, and Prof Halim, our head nephrology, suggested that we do tidal peritoneal dialysis, meaning that when we do peritoneal dialysis, usually we clear all the fluid, right, from the patient peritoneal membrane, but peritoneum cavity. But we don't do that. We clear uh, uh, some of the fluid out, and we dwell some still, and we keep exchanging the fluid about 1.5 liters every time, every 4 hours, tidal dialysis, so that the amount of fluid that we need to pump in is less every time, and the amount that of fluid that the patient needs to carry is also less, and the amount of fluid that settles in the patient's body on average over time is also less. So it's actually less stressful for the patient body because the technology is focusing on young patient that is still productive but now limited by the disease. They cannot go to work, they cannot do their daily activities. So hopefully with portable dialysis they can. All right. So the focus would be working adult with end-stage renal disease (ESRD), active and mobile patients, where the patient travels a lot, and also older patients that wanting to travel. So hopefully this device would help the older patient to do travels and not tied to their localities because of their disease and their requirement to do dialysis 3-4 times a week and so. Okay, and that's going to be our target market, and from that we develop our prototype, keeping portability in mind. Of course, the first prototype, this is back in 2018, I think it's quite sizable, quite big, and before we initialize the pumping technology, and then the dialysis still carries about uh, 5 liters of fluid, which is quite bulky for an older patient actually, especially to carry. Then we improve, making it smaller. The battery life is the main technology that we have to tackle. We still have to use lithium ion battery, and the weight is reduced. And the key to the module is all the sensors and the sensors that can detect the condition of the fluids in the human body. So after that, we improve to the third prototype where the sensor module is much improved. And currently we are using IMAN sensors to do that, and the pump module is much improved. The third version still uses peristaltic pump, but it's not as smooth as the current version. And around 2020, in the beginning of COVID, I think we completed our device. That's the final device that has been registered under the Malaysian MDA, Medical Device Authority. And Malaysian MDA heavily rely on the certification standard of European EIC. So whatever we certify here is at par with what is certified based on EIC. So this device just a bit of it's a cycler, and we have improved the cycler to become an automatic peritoneal dialysis system (APD), and basically the pump in and pump out rate is about 90 to 180 milliliter per minute. This is taking into account that the machine does not have to pump fast because the dwell time is less, and the dwell amount is also less in tidal peritoneal dialysis system. So sometimes we dwell for only 1 hour, depending on the condition of the patient, usually around 3 hours. And the tidal amount that we have in the body is around 1 to 1.5. And we pump in 1 liter to 1.5 into the body, depending on the body weight, size, physical condition, concentration of the dialysis, and so on. So the sensors have flow rate sensors, bubble sensor, and occlusion sensors embedded into the, this is the theoretical device. So the sensor sits inside, and this is actually our sensor, ion sensor, our institute sensor that we developed and integrated into the device. So it is small, it is lightweight, and it is easily portable. That's the goal of the innovation. And treatment can be done on the go while working, driving, walking, and exercising. We did clinical trials. Now we are halfway into the phase 2B clinical trial where we try at home or in real working condition. So the patient would be attached to the machine in the morning before breakfast, maybe 6 a.m., 7 a.m., and then the next cycle would be during lunchtime, 12 p.m. So the patient can work in between, and the next cycle will be 6 p.m. And each cycle is about 27 minutes. And that really is doable for our patient. And the device itself is connected to the app, and the app is connected to the cloud. So the device really is not controlled by the patient, but rather the prescription comes directly from the doctors. The doctors key in the patient requirement in the GUI, and when the patient turn on the device, is directly connected to the cloud, and it updates the prescription. And the patient can only press start. Once the device started, it follows whatever prescription that the doctor sets real time. And one important thing for PD is infection, right? That's the biggest issue. And we install a sensor that can detect the condition of the effluent, so that the density and the opacity of the effluent would give an idea to the doctors online whether the patient is doing well or not, whether the patient has infection or not, and so on. Okay, we have partners with our hospital, and KKM is actually the Ministry of Health of Malaysia, and we do the machine just like the current systems in the market, where is prescribed by the doctors and serviced by a separate company, Fokko Group, that do the service monthly, bi-monthly service, and so on. And we target mobility, and the customer segment is actually working young middle-aged ESRD patient and active young adults. So that's just a bit to give you an idea of how much it costs and so on to run the system. And the user are recommended by the nephrology consultant. And in Malaysia, cost of treatment is usually borne by insurance or healthcare providers. Lembaga zakat, for example, KWSP is your 401k in the US, or your retirement plan. And we target Malaysian PD market first, because we have around 50,000 patients on dialysis right now, about 20% on PD, 80% on HD, but then the aim is to focus on PD more. If we can tackle home dialysis issues, related issues, infections, and so on. So that's why we are focusing on younger working adults, where hygienicity is less a concern, where they can actually maintain and ensure sterility of the system, because they are quite young and they are quite educated in terms of sterility and also hygiene. That's a bit about the device. It is designed to be portable. It's connected to your peritoneal catheter, and it has accessories that come with it. Generally, patient carry 1.5 to 2 liters of fluid, and it focuses on young patients. And when we tested, none of them complained of the burden of carrying some fluid with them. But of course, later on, like I explained before, we are moving into a fully regenerative fluid, solvent technology, and so on. That's just a bit on the machine. Just two times accelerated video of the pumping. Is a cycler, right? It's a smart cycler basically, and we have improved the system. I'll show you later on. Yeah. To become APD. So these are some trademark and pattern that we have on the product. Malaysian pattern, and the trademark name is Care, and it's actually awarded Comstat Best Patent Award in 2021 among 56 OIC countries, and that's your IEC certificate. We go all the way to IEC 60601-1, -1-1-1-2-2-39 for peritoneal dialysis system. So this is what I was talking about. IEC 60601-1-1-1, medical electrical equipment general safety, -1-2, medical electrical equipment basic safety and essential performances, 60601-2-39 for peritoneal dialysis. For us, this is the hardest one to get, peritoneal dialysis equipment. And we have ISO 13485 to manufacture the product within by our university, by our institution. And then we have MDA, Medical Device Authority certification, and the Medical Device Act 2012, and also NPRA, National Pharmaceutical Regulatory Agency of Malaysia. So some of the portable peritoneal dialysis system Care clinical trial, that's actually the first one. If you can see, we still try to comply with Fresenius system, but then now we have our own dialysis already and our own transfer system already. That's independent of any other system, but we can use our device into the current system, but we also now uses our own system for the whole dialysis. And our commercialization partner is the Prof Group. It's a spin-off actually from the university, and now it's a producer and manufacturer of biomedical products in Malaysia. That's the 2.0 version of the device, where the bottom part, actually this module right here, this guy right here, can control the cycler, which is the top guy here, can control the machine so that it perform like APD. Just like your APD that you have in the ward, it can perform all the function similar and better. So we are doing clinical trial for this combo right here, this whole system right here, and then we can do APD CAPD, automated CAPD, which we call PAPD, and also emergency dialysis with the whole system. So I think that's all that I want to share with you guys. If you have any question, you can contact me. Azlan Hamzah at ukm.edu.my. I'll share the contact later on. This is basically the system that we have. Okay, you can see. The top is just the cycler and the controller, and is embedded with the sensors. So that's the optical sensors that we develop in-house in Iman, where we are manufacturing microengineering and nanoelectronics. So that's kind of our specialty, and the patented pumping system and the whole cycler device, and also the automated module. So that two devices would act as a full APD system on the go. So you can actually carry this much easier than the current dialysis system. The total weight may be less than 3 kilograms. So it's easy to bring, except for the connectivity, which you still have to do with, but you can use other system as well as our system. Okay, I think thank you very much for this presentation, for this slot, and I welcome any question. Thank you.
Thank you for this opportunity to present at this meeting. It's a special time in the world, and I appreciate the opportunity to share our work on developing an implantable artificial kidney with this audience. Please note that this work is under the auspices of what we call the Kidney Project, and it's a collaboration between multiple parties within the United States and hopefully other members in the world. But for now, our team is located primarily in the United States and led by the University of California, San Francisco. So what is it that we are trying to do? Our goal is to build a device that provides total renal replacement, very much like a kidney. And in our case, it will be an implantable bioartificial kidney. The vision for this device is shown on this slide. It will be totally implanted, very much like a kidney transplant. It will consist of a filtration unit coupled with a cellular unit. The filtration unit mimics the glomerulus, while the cellular units mimics the kidney tubule. And by bringing in electronics, we can also monitor the device performance over time, but also monitor the patient's health. Once this device is put in, our vision is that it will provide continuous treatment to the patient, allow the patient to be mobile, no need to be tethered to a dialysis machine. Because the device is totally implanted, it will have minimized risks of infection relative to dialysis, where you have a through-the-skin connection. And the cellular unit will provide more physiological therapy than dialysis does. And the cellular component is protected from the patient's immune system, such that you would not actually need immune suppression. In our vision, this device is autonomous, operates 24 hours, 7 days a week, and should allow the patient to eat and drink freely and have an improved quality of life. So as we develop this, we request input from clinicians on not our device, but just what they would want to see in next generation renal replacement therapy. So we invite you to take a survey that's going to be distributed worldwide to understand what are the physician preferences for such types of devices. And this survey will take you through a series of questions, which will then collate and help inform not just the development of our work, but make it available to the community as to what is important to clinicians for next generation renal replacement devices. So please take this survey and give us your input. It's instructive to look at what the native kidney does. The native kidney has a number of functions, obviously. We focus on two, filtration and reabsorption. And taking an engineering view at the kidney, we can break it up into a filtration unit, the glomerulus, which I call in our device the hemofilter, and a tubular unit, the renal tubule, in which in our device we call the bioreactor. And as many of you are already familiar with, a healthy kidney generates about 150 liters of ultrafiltrate daily. But we only pass out a liter or two as urine because most of that ultrafiltrate is reabsorbed selectively in the tubule, and the remaining water concentrates the toxins into urine. So what we'd like to be inspired by is, can we actually take this knowledge about how the native kidney works and use it to engineer a medical device that provides replacement function? As any other engineering project, it's an ambitious goal. So we decided to initially talk with patients and see, what do patients really care about? And this was a summary of our survey that we did a few years back, and it was published in the journal. And what we learned was that patients are so distressed with going for dialysis and all the complications it brings about that they would be willing to accept an implanted device, even at a slightly higher risk of mortality, but if they could be completely mobile. Not only that, they're willing for a device that does not provide all the functions of a full kidney, but as long as let them be mobile and have a higher quality of life. So using this information and some of the information we got from our clinical colleagues, we ended up coming up with specifications for what an implantable artificial kidney may look like. And we call this a minimum viable product. So the total size of the device has to be such that it can be implanted in the human anatomy. We must pass out enough clearance to keep a patient healthy. And based on our conversations with physicians and on patients, a clearance of 30 milliliters per minute was more than enough to keep a patient off dialysis, as you all know, but also let the disease be managed, chronic kidney disease be managed by lifestyle changes and medications. So as a minimum, if we can achieve somewhere on the order of 20 to 30 milliliters of urea clearance, while making sure that we still pass out urine of 1 to 2 to 3 liters, that would be acceptable for patients and physicians as a minimum viable product. And the device has to remove these electrolytes and maintain balance, homeostasis in the body. So using this information, we identified specifications that the hemofilter has to provide a certain amount of clearance, and the bioreactor has to selectively reabsorb and maintain electrolyte balance. So with this, we can then start moving towards the steps needed to engineer such a device. To guide us and inspire us, work that was done almost 20 years ago at the University of Michigan was very helpful in how we could design our system. Here's work done by Dr. David Humes, who had developed a system he called the renal assist device to provide treatments to patients in the ICU with kidney failure associated with sepsis. And he took conventional dialyzer technology, but connected them in the architecture of a nephron. In this case, the first dialyzer was performing hemofiltration. In the second dialyzer, he actually lined the lumens of the hollow fiber dialyzer membrane with cadaver kidney cells to mimic the tubule. And he was able to take this through phase 1 and phase 2 clinical trials and is able to show that there's actually a survival benefit for patients. Here's the device system in the ICU. You've got all this infrastructure, but what is remarkable is that the patients that got treated by this renal assist device experienced 50% decrease in mortality relative to standard CRRT, and it could be attributed to the use of cells in the bioreactor. Clearly, this is a very impressive achievement. However, this is not practical for chronic kidney failure patients. So that allowed us to think, how can we take that breakthrough, demonstrate in the clinical research setting, and move it to something that could be used by chronic kidney failure patients, allowing them the benefits of kidney transplant without the issues associated with getting a donor organ. And that is the work that has been known as the Kidney Project. So to move from the left, which is the system in the ICU, to a totally implanted system that operates autonomously in the body, we have to leverage state-of-the-art technology. And for this, we look towards semiconductor nanotechnology, the same technology that's allowing me to communicate with you, electronics, wireless. We're making the hardware for computer chips. So by using the technology for computer chips that allows us to miniaturize sophisticated electronic circuitry, perhaps we could then miniaturize the renal assist device into an implantable bioartificial kidney. And the fundamental breakthrough to make that happen is a next generation membrane. You cannot use the conventional dialyzer membranes for an implantable device. And so we ended up developing a new membrane technology using semiconductor silicon that we call silicon nanopore membranes. And here you see a silicon wafer patterned with slit pores using technologies from a semiconductor manufacturing. These membranes have a high molecular selectivity. That means they discriminate very well between different sizes of solutes. They have a low fluidic resistance. They don't require much energy to generate filtrate. And they can be made in a factory, not in a mass manufacturing way. So it's not just something that will stay confined into the research environment. It's instructive to compare how our membranes, the silicon nanopore membranes or SNM, compare with the standard dialyzer membranes made from polysulfone, the hollow fiber membranes. On the left-hand side, you can see a cross-section of a single dialyzer filter that's used in a conventional system with our silicon nanopore membrane. You may note that our membrane is much thinner. The pore sizes are much more uniform in geometry, and this leads to two advantages. One is our membranes have a very high hydraulic permeability. Basically, what that means is that you need very little energy to generate ultrafiltrate. In fact, you can generate enough ultrafiltrate just using blood pressure alone. You would not need electrical power. Second, the uniformity of the pore size allows us to discriminate between desirable solutes, such as albumin, and undesirable solutes, such as urea. And by having a very sharp cutoff, our membrane allows that selectivity, which means we can actually achieve improved clearance. So our membranes make it possible to think about a system that does not require electrical power, but just relies on blood pressure, and then performs removal that's very much comparable to the native kidney. And in fact, we tested the selectivity of our membranes where we took a super physiological concentration of various biomolecules, including cytokines, insulin, glucose, albumin, and then we tested it on our membrane. And this graph shows the sieving coefficient, which is basically a way to show what goes through versus what doesn't go through. We had no passage of albumin or antibodies. We had almost 100% passage of glucose and insulin. And we also did not see the evidence of any degradation of the material. What this tells us is that we actually may have a system that can allow us to put the cells on one side of the membrane such that it's protected from the patient's immune system, opening up the road to avoiding the need for immunosuppression. This work can further be tuned by modulating the pore size such that you actually remove the passage of even smaller molecules or larger molecules as the case may be. In this case, over 6 hours, we did see some passage of cytokines, and that can be adjusted by modifying the pore size and the coatings. We also looked at how do you make these membranes biocompatible so they don't have issues with blood clots or get blocked with proteins over time. And what you see in this graph is we are able to compare membranes in case that are coated, in this particular case with a Zwitter ionic polymer, polysulfobetaine methacrylate, PSBMEA, compared that to an uncoated membrane, which you see on top. And you can see the comparison is that there's almost no debris of cellular components in blood on the membrane material. In contrast, the uncoated does have some debris. And in the graph on the left, what you see is quantitative analysis of how our membranes resist protein adsorption. And they retard them such that we can open the door to having a system that does not require any anticoagulation for operation. We also looked at where do we achieve the cellular component function. We have to look at kidney cells. So in this particular case, we have worked with colleagues to source kidney cells from human cadavers. And my colleagues have developed protocols that by taking kidney cells from cadavers and applying cell culture protocols, you can expand them and generate billions of cells. And what you're seeing on the graph here is cells that have been expanded by an average protocol, which you call the average and the black, and an enhanced protocol, the EP designation. And each of those lines are different donors. And you can see, especially for the green line, which is a healthier, younger donor, the cells proliferate a lot more. But he has a strategy to actually increase the number of cells from just a gram biopsy and get more than enough cells for many artificial kidneys, presumably thousands of artificial kidneys. And in the little picture in the inset, what you see is the ability of these kidney cells without protocols to grow on the membrane and exhibit the phenotypes of kidney proximal tubule cells, including tight boundary junctions and cilia that are mechanosensors of these cells. So in summary, we've got a source of cells that we can use for a device, and these cells can be grown in culture and expanded over and over again. And of course, we're not limited to human cells. We can also look at xenogeneic cells if there's ever interest, or as the stem cell field moves forward, also incorporating their cells into our device. So we've taken the knowledge we've generated to date, which is making a filter, getting the cells, and said, let us do a proof of concept experiment where we integrate the filter unit with the cellular unit. And you're seeing the computer-aided design image on the left. On the right-hand side, you see an actual prototype we've developed. It's about the size of 2 decks of cards. We've taken this device and put it into a preclinical model, in this case, porcine, pig. And what you're seeing here is this is surgery, during surgery, the hemofilter and the bioreactor being connected with blood to the blood vessels, the iliac vessels in this case, with vascular grafts. You've got the purple tube that goes to the bladder, which is where the output of the artificial kidney is intended to go. And on the top left, you see the device where it's passing and processing blood, and on the bottom is after surgery. So this is exactly analogous to what a kidney transplant surgery looks like. You're putting it in the fossa region, you're connected to the iliac vessels, and you have a third output to the bladder. We put this into the pig, and at the output of the bladder tube, which is the input to the bladder, we can clearly see the generation of a clear fluid. And I call this proto-urine because it's being generated from the hemofilter, being processed by the bioreactor. And here we've got clear fluid that does not have albumin as the hallmarks of urine. We conducted this test as our first preliminary test for 3 days. The pig did not have any anticoagulation and it did not have any immune suppression. You'll notice that the amount of output of our device is very small. The filter unit provides only 4 microliters per minute. But as a proof of concept, that was very exciting. And what was even more exciting was that the cellular bioreactor had absorbed much of the ultrafiltrate, very much like it does in the native kidney. And despite no immunosuppression, the kidney cells inside the device were as viable as the ones outside. And we maintain viability of these cells to almost 95%. So to summarize this work, what I would like to end by saying is that it is indeed feasible to construct an implantable bioartificial kidney. It is possible to do so because we've taken a technology-based approach where we take the known science, apply it to build something that will focus on patients' needs and doesn't have to be 100% native kidney, but provides enough clearance such that we avoid many of the morbidities associated with dialysis, but also provide an improved quality of life. To achieve this, we cannot rely on the standard dialyzer technology. We have actually leveraged the knowledge from electronics and electronics miniaturization, where they take sophisticated electronic circuit and by using semiconductor manufacturing, create chips. And that's the same paradigm we can use to make an implantable bioartificial kidney. And the goal of our work was to demonstrate the feasibility of this approach and in an implantable format, being inspired by the work that was done almost 20 years ago in the ICU. And we did successfully confirm that a combination of a bioreactor and a hemofilter will allow the production of urine. So with this work, I thank you for this opportunity and acknowledge all my supporters for funding, as well as collaborators around the country, including Dr. William Fizel, who is my clinical partner on the project. Thank you very much.
Hello, this is Fokko Wieringa from the Netherlands, trying to tell you a little bit about some visions on miniaturization towards implantation and a roadmap for disruptive kidney technologies. First of all, I work for IMEC. I'm 100% employed by them. IMEC is a not-for-profit research hub for nanotechnologies, and they also hire me as a consultancy to NeoKidney, the NeoKidney project, which is working on a portable artificial kidney, a portable hemodialysis machine that fits in hand luggage for the airplane. Also, the Dutch Kidney Foundation hires me as a consultant for about 5% of my time. 10% of my time, I'm an associate professor in the UMC, the University Medical Center of Utrecht, at the nephrology department, but I am not a medical doctor. I'm just a technologist that tries to make medical devices. They elected me as a chair for the Workgroup 3 Breakthrough Innovation of the European Kidney Health Alliance. And I also represent the Netherlands in IEC and ISO standardization workgroups on standards for instance, hemodialysis and peritoneal dialysis machines. So much for the declarations. Well, like I said, I work at IMEC, and we are pushing the boundaries of what is possible with chip technology. This is one view in one of the corridors in our clean room in Leuven, where we make all kinds of experimental chips and pushing the limits of what we can do with modern chip technology. Now we have two projects which are called KitNew and NextGen High Tech, and both of them are working on artificial organs, in particular artificial kidneys. You may not know IMEC that well, but no matter what brand of mobile phone you have, there will be at least 5 patents of IMEC in there, and some chips that we designed originally. But we don't make products. We license our discoveries and our patents to manufacturers that use them in their products. Now, as this is all about innovation and miniaturization of dialysis solutions or implantable artificial kidneys, let's take a look at how it started. This is a photograph from the Netherlands. This is not an actual dialysis session, by the way. It is head nurse Maria Terwelle who is posing as a patient. But the machine is real. This was the very first working hemodialysis machine in the world. Some attempts were made before, but this was the first one that really worked. And this, say, in 1945, hemodialysis really took a launch from the Netherlands with Dr. Kolff treating Sophia Schaffstadt. Now, this is a 1945 computer. Basically, it's not even one computer, it's only half of it. This is what nowadays would be the keyboard and the screen. So this is one half, this is the input section. The other half of the machine is on the other side of the corridor and not even on the photo. But you see, computers were quite big and they couldn't do that much in those days. Now, why am I talking about computers? Because I should be talking about artificial kidneys. Well, here we see a photograph on which we see a hemodialysis machine and we see a computer nowadays, 2025. Okay, the hemodialysis machine is maybe not the most modern one, but you get the picture. Now the computer shrunk incredibly. It became much smaller, but it became also much more powerful and more energy friendly and portable. Whereas the dialysis machine, well, it got a little bit smaller, maybe a little bit more reliable, but nevertheless, it's still a big thing. So what happened? That's one question we'll answer today. And another one is that yearly on plastic tubing waste for dialysis only, we can go several times to the moon and back if we put it all behind each other per year. And this is a slide that I thank the University of Washington in Seattle for, because they made this wonderful figure. And also we have to realize that one hemodialysis patient on average uses 156 pallets of clean water per patient per year, 165 of these pallets. And even worse, only 1/3 of this water actually reaches the patient on average. 2/3 of that water is wasted in the reverse osmosis installation that usually makes the dialysis water. So that's pretty much water, much more than one person ever would drink in a year. On energy, we have the same kind of weird comparison to our kidneys. Hemodialysis takes about 3 to 5 kilowatt hours in a time of 4-hour session. But in that same 4 hours, our whole human body takes about 0.3 kilowatt hours. That's also, you see the difference in energy consumption between the whole body and a very poor replacement of a kidney. Now, there was, of course, a few years back in 2018, we released a technology roadmap for innovative renal replacement therapies with the Kidney Health Initiative. And FDA put great effort on this to make it work. And I'm very thankful that we published this roadmap. And we're also working on an update for it again. And this roadmap played a big role in the following movement, the Decade of the Kidney, that is initiated by the American Association of Kidney Patients together with the Kidney Health Initiative in America. And they had a round table in which they, well, a figurative round table in which they had industry leaders, the White House people, the National Institute of Health, the FDA regulatory people, the academic experts, and the nephrologists that do research, the payers, the CMS, which is paying the bills for the and the insurance companies for health, and the American Society of Nephrology, and Home Dialysis United. Those are a few of those parties that were on that round table. And they managed to write that roadmap. In 2018, it was published. But on behalf of the Dutch Kidney Foundation, I also worked from the other side of the ocean quite a bit on that roadmap. And guess what? In Europe, we have the same kind of round table. We have the kidney foundations, we have the European Renal Association, we have the International Society of Nephrology also taking part, the nurses, nephrology nurses, and the patient, of course. Those are the most important ones. The European Kidney Patient Federation, they're all on that round table. So interestingly enough, we see two round tables on two sides of the ocean, which independently took shape. Now, we also have a twin sister of the Kidney Health Initiative in Europe, namely the European Kidney Health Alliance. They're more or less twin sisters. They want to improve the conditions of the kidney patients. And in America, they have a Congressional Kidney Caucus. That is a group of politicians in Congress that are, taking care and trying to stimulate innovation for kidney patients. They also had a Kidney X program, a prize program, in which you could win prizes for trying to get innovations done. I had the luck to also win one of those kidney prizes, Kidney X prize. And that was quite remarkable that they even gave a prize to a non-American party. In Europe, we have the members of European Parliament group for kidney health. So also here we see a mirror symmetry between the politicians. And via this Patient Voices Bridge Oceans Decade of the Kidney Initiative, we brought those two groups in contact. So the Congressional Kidney Caucus from the US and the European members of the European Parliament for Kidney Health, they spoke to each other via teleconference, and they agreed, hey, we have the same kind of target. We want to improve the health of kidney patients. Why wouldn't we work together? That's a great idea. And meanwhile, we have this European program called KidNew, in which I helped to take part. We have a Dutch national growth fund, NextGen High Tech. And there we also communicate with the existing structure of the artificial organs federations. So the International Federation for Artificial Organs combines the European, the Japanese, the Asian Pacific, and the American Society for Artificial Organs. And if we combine those silos, we can get things done. That's the idea. KDIGO recently in Berlin in April this year also joined this structure. But okay, where are we now? Enough about all kinds of institutions. Where are we now and where should we be heading? Well, this is an illustration from a recently appeared article in the American Journal of Kidney Disease. The link should click, if you have the PDF, you could click the link. And there we see that, well, transplantation, of course, is the best we have from human to human. But there's also work ongoing on cultivated kidneys or xeno kidneys, xenotransplants that we would grow in animals. And the big advantage here is that you don't need dialysate, you don't need electricity, you simply can walk around and be whatever you want because you have a transplant. Xenotransplant and cultivated kidneys, they're still a bit away, although xenotransplants have been done and patients even went home with that. Survival is still limited, but it's clearly making progress. But okay, the other, suppose you cannot even be transplanted, which is also sometimes the case with patients, then at least we have a hemodialysis and we have peritoneal dialysis, so B and F. We have that, but we could miniaturize that quite a bit if we would reuse the dialysate. So if we would purify the spent dialysate from the toxins, make it as good as new and reuse it, that would save a huge amount of water, which also would save a huge amount of electricity because you don't have to heat up the fresh dialysate again. That would help the engineers to make your device for hemodialysis or peritoneal dialysis, we can do the same trick there, to make it smaller and more portable. That now is ongoing. There is clinical trials in progress for the next kidney that is for hemodialysis doing exactly this. There's also a device in still clinical trials from Singapore, which is using regeneration of dialysate for PD. And also in the Netherlands, there's the WeKit also in clinical trials. But we could even go further. If we go to to D, there we would be able to say, let's make an implantable hemodialysis filter. So instead of taking the blood out of the body, the blood would stay in the body, go through the filter, which is implanted, and only 2 catheters for the dialysate would go through the skin. And of course, preferably, you'd like to take dialysate, which you can regenerate there because, hey, that's, of course, more compact. That would already be quite something because then you don't have the needling for your blood. It simply would stay in the body. And if you would do nocturnal dialysis, hemodialysis, and one of your return lines would go loose, doesn't matter. You get a wet bed, but no bleeding. And that is a huge step forward. So that would be helping, for instance, for nocturnal dialysis. And the very, very future music for the technology part might be that you not only have a hemodialysis filter, but also tubular function emulated by, for instance, a bioreactor, which might be implanted. Then you would need no dialysate at all, and you simply would pee. Of course, not getting any kidney disease or getting a transplant is still better, but not everybody can get a transplant. This is where we're standing now. And this is the wonderful hospital of the academic hospital of Utrecht University, where I have the luck to also be part-time associate professor at the nephrology department, together with Karin Gerritsen, Roos Mazerio, and of course Marianne Verhaar, to name a few. This is a really great hospital where good research is being done, but I'm biased, of course. But come over and visit us, you can see. So what we try to do is to get rid of these technologies and miniaturize them. The first step, let's first take a look at a single pass, typical single pass normal machine as they are now. We take the blood from the body, we pump it through a dialyzer. We also have a huge amount of water that we take from the line. We purify that, we mix the salts, we throw it in the big reservoir, we heat it up, we pump it through the filter once, and then we throw it away in the sewerage. We throw it away to the drain, which means we throw away a huge amount of water and a huge amount of electricity that we needed to heat up that water. That's how it is now. Single pass, loss of water and heat down the drain. But what if we would regenerate this? So like I said, let's regenerate the dialysate. First of all, you'd need much less fluid and also much less electricity because it's already warm. You regenerate it, but it doesn't cool down fully there. You only need to heat it up a little bit to compensate for heat loss. Suddenly your machine becomes much more compact and also much more transportable and less dependent on infrastructure. Because let's be fair, the big machines need a very good infrastructure on water and electricity, whereas this thing needs less from both. So the regeneration of dialysate is an interesting way to make your devices smaller, but it's not implantable yet. But at least it fits in a suitcase and you can take it with you. But let's be fair, it still needs a needle or a catheter. And people don't like that. So the wise guy here said, wouldn't hemodialysis without needles be great? And the patient here says, I fully agree. I really am in favor of that. We wonder why. Well, that may come quite close now. The technologies are already there. Suppose we would take the next kidney machine, which is regenerating the dialysate. So in this part of the machine with the dotted lines, you see the regeneration part. What if we would implant the filter, then we could get rid of the left part of the machine, which is the blood circuit. There was quite some interesting discussions going on when we met each other, and it was by coincidence at the Next Kidney booth. So it would look like this. Only half of that machine that you just saw would be needed externally, whereas the hemodialysis filter would be implanted and the heart would be the blood pump. You don't need a blood pump anymore because the filter will be directly placed from artery to vein. Only thing externally would still be the dialysate reservoir. Imagine that would get rid of the blood circuit, the disposable blood circuits. You would not throw away 156 of the filters and blood circuits a year per patient. Only the dialysate circuit would be needed. It gives you even more freedom. Now, of course, I can imagine that people would say, that's impossible. That's simply not possible. It's never going to work. It's never going to. You cannot clean the blood inside of the body. You have to bring the blood outside of the body and there clean it. But hey, what do our natural kidneys do? They apparently are able to clean the blood inside the body. So let's not call it impossible, but think on how can we hammer it down? Well, we can apply the laws of Arthur C. Clarke. Arthur C. Clarke was a scientist technician that invented many things and predicted in his science fiction novels also many scientific developments that actually came true. And he applied always 3 rules in everything he did. Namely, a distinguished but a bit elderly scientist that states something is possible is almost certainly right. But when stating that same scientist something is impossible, he or she may be very probably wrong. Sounds crazy, but we've seen history full of these examples. Now, and the only way of discovering the limits of the possible is to venture a little bit into the impossible. And the third one I like so much, any sufficiently advanced technology is indistinguishable from magic. So one of my PhD students who became a surgeon and later a surgical professor, he wrote down, if you combine physicians with technicians, you get magicians. I like that quote very much. So if we apply those 3 laws of Arthur C. Clarke, we can make the impossible become possible. Now, of course, that's a nice word game, but how do you prove that? Well, the interesting thing is that hemodialysis filter without the need for a blood pump already has been shown in history. 2 of these examples are here. Parallel plate dialyzers. They are driven by heart pressure. No blood pump, just the pressure from artery to vein by the heart. This is the Skaggs-Leonard's plate dialyzer from 1948 already. And this is from 1960, the Kiel plate dialyzer. It was a Norwegian invention. They both could be driven without an external blood pump, just on the heart pressure. And the Kiel one, although it looks very big, only had a priming blood volume of smaller than 300 milliliters, which is quite reasonable for such a big thing. Very thin layers of blood were dialyzed across cellophane. So what if we change from fiber-based filters, which require huge pressure and thus a blood pump, if we would go to parallel plates again? Let's go back to the future. That's what I try to say. I already grew the gray hair. It has to be a little bit longer, and I have to look a bit more difficult, and I have to find a guy named Marty and one of those futuristic cars, and who knows what we get. Well, at the moment we're this far. We have chip technology where we miniaturize the functionality of fiber-based filters onto flat plates made from silicon, from chips. I'm not the only one that does that with our group. Also the group of Shuvo and Bill Fazell in the US, they also are working on the same ideas, different chip technologies, but the same idea, using chip technologies for the filters. Our queen, Maxima, together with the Minister of Health and Economics, they both went to the US and they looked upon this work. And well, it was said there, if the Netherlands would at least use the miniaturized dialysate pump with the recirculation, we could combine it with the implantable filter from the US. Now Europe is also working on an implantable filter. And to be honest, we'd like to work together some way. Probably together we can come further quicker. Now, the Kidney Project makes chip filters which have slits there. This is a 200 nanometer scale bar at the bottom. And you see those slits are extremely narrow. And then they have quite a length here. These are slits. And the KidNew project and the Next Gen High-Tech project in Europe, IMEC in their clean room makes these filters. They have tiny holes. There's also a 200 nanometer scale bar here. You see that this photograph, the right one, has about double the size, double the magnification of the left one. But you get the difference between. Both are chip-based. And here you see a typical diagram of a fiber-based dialysis filter with holes like that. And what you see here is that the holes in a fiber-based dialysis filter are varying in size quite a bit. There's a huge variation in size, whereas to the left or to the right, in both cases, the sizes of the holes, the passage of the molecules is much more strict and uniform. Which means that if you have a very uniform size of your pores, that means that you have a much steeper cutoff. And that would be interesting. So the red curve here would be what it would look like. And that means albumin is retained. You don't lose albumin, but you do get a huge penetration of medium-sized molecules. And that is very interesting because normally the other filters are having a much less steep cutoff, or they even lose albumin. And in this case, you can have the best of both worlds. No loss of albumin and still a very good passage of the large middle molecules. By the way, note that the average diameter of a human hair is about 250 times the size of that 200 nanometer scale bar here. So we're talking about incredibly small holes, but they're all the same. Now, if you're working on a chip, you can of course make a filter, but that filter can also be made smart because the same technology that is used to make the pores is also compatible with technology that can make electronics. So why not make electronic sensors on board that would, for instance, measure your sodium, potassium, calcium, creatinine, urea, and so on, pH, temperature. You can go on that. And if you put them on the same filter, you wouldn't even need the blood work to take blood and analyze the electrolytes and the urea and creatinine. Why would you? The implantable filter would already analyze it for you. So you would get more data and no blood taking also for that. So what we envision that might be what the future would look like is that we take silicon chip technology to make the filters, to implant at least those filters, to put some smart electronics on there to measure blood pressures, flow, temperature, some electrolytes like sodium, potassium, calcium, pH, and have a wireless connection so that we wirelessly can measure what's going on inside and that we can transmit that via, for instance, Wi-Fi to a computer network, and that the nephrologist and or nurse practitioner can look at those data remotely. So you'd have to visit the hospital less, you'd have more freedom to move, whereas the medical professionals would have, via telehealth, much more data. That would be, I think, a great future vision. From a technology point of view, it's possible. It's just how much do we want it? Now, one step further would be a fully artificial implantable kidney, which would not only mimic the dialysis filter, because basically a kitchen sieve is more or less depicting here. The dialysis filter is not more than a kitchen sieve with very tiny holes. But if we also have a bioreactor, a tubulus, that would sort out the bad stuff to prick into the urine, and from the pre-urine, keep the good stuff, that would help us to actually simply have normal urine or almost normal urine coming to the bladder. We would need no extracorporeal connection at all. It's much further future, but still, I would be so happy to see that if I would be a kidney failure patient, that my only worry now is how to get on the airplane instead of say, hey, what's that on the X-ray? There's something in your body, that's just my artificial kidney. Now let me through. If that's your only worry, you're already far. So to summarize, I think the road towards an implantable artificial kidney would grossly be helped by chip technology. We would definitely have better chances to get that running. It would function without immune suppression, much more equal throughout the week, much less fluctuations in your overload in fluid and also electrolytes. You would have more freedom to move, no needles anymore because the filter's in the patient. Saves a lot of water, it saves a lot of electricity and transport time. And of course, these nanoporous filters, they should be coated with extremely blood compatible coatings because they have to be in there for years. They need wireless charging for the electronics and telemonitoring, sensors, actuators, and a control unit. But those electronic aspects, they can be taken into account quite quickly. So the sweet spot between a health program, a Green Deal, and a CHIPS Act program would be exactly this. Now, if you want to read about this, because this is just a PowerPoint and a small talk, you can read this article. It's freely accessible in the internet. And if you get a PDF, the link should work there. But I can paint a picture of the future. But let's be fair, it's not there yet. And why not? Well, that mainly depends on the funding. I'm going to introduce you to the triangle, the famous triangle of project management. So what you see is a triangle, and you can choose 2 points of the triangle. But if you take 2, the third one automatically is falling off. Now, of course, in medical technology, high quality is not negotiable. It is clear that we need high quality. It has to work properly. So somewhere in this upper triangle, we have to be. Then you can choose between let's do it quickly or let's keep the funding low. Let's try to keep the money low. Well, if you are a patient, you dream about doing it quickly. That is what patients would, especially if you consider that the average survival time of, say, a patient on hemodialysis is about 5 to 6 years. You'd like to see things change for the better quickly. But the reality is that there's extremely low funding for realization of such modalities, which means if you're not paying too much money on there, it's going to take a very long time to see progress. And that is something that politicians also have to realize. Policymakers always ask me, oh, Dr. Wieringa, you tell a wonderful story. So when can we have it? And the answer is, when do you want it? Because the quicker you want it, unfortunately, the more money it will cost. But if you don't give any money at all, it'll take forever. Not just for kidneys, that's also for a highway or a bridge or whatever you want to build. So my plea today is we should bundle the best brains of the world to build better treatments. So we have to bring together the patients, the doctors and the nurses, the policymakers, inventors and investors, engineers, of course, entrepreneurs, and unite them in the decade of the kidney, which is not just an American initiative, but it's also joined by the European Kidney Patient Federation and the European Kidney Health Alliance. And we'd like to see this worldwide happen. And we also need to create a solid funding program. And you believe me, financial engineering is an engineering skill and is badly needed for innovation on this. And there we have the last thing. Of course, this is a cartoon. It's meant to be funny, but there is a simple truth in it. Of course, you can have the similarity between a euro symbol and grow a kidney from it. It's funny. But realize that this symbolizes that it also works with dollars and pounds and yens and whatever. I would have some doubts about rubles at the moment, because I don't think that would be a good country to work with at the moment, given how they behave. But still, there's plenty of other countries that could work together quite well and get this job done. So if anybody wants to reach me out on trying to work together or exchange ideas, this is how to reach me. I'm proud to work at IMEC and with the UMC Utrecht, be part of the European Kidney Health Alliance and the Decade of the Kidney. And I'm so happy that the KidNew project funded by the European Union and the Next Gen High-Tech Artificial Organs program funded by the Dutch government are existing and going on strong. Thank you very much for your attention, and feel free to reach out.